joint seminar. Today we are very happy to have Dr. Jen-Tsung Hsiang to give the talk. Dr. Hsiang received his bachelor degree in physics from our university, National Taiwan University, in 1992, and then received his PhD degree in physics from Tufts University in Massachusetts, USA. Then after that, he was a postdoc at various places, and in 2014, he was a research fellow at Fudan University in China, and then was a visiting associate professor at University of Maryland from 2017 to 2019. And he is now a research fellow at the National Central University. So let's welcome him.
Thank you, President Wang, for inviting me over here to report our recent research on thermodynamics. Yeah, in a sense that thermodynamics has been, at least for the recent year, it has been a kind of integral part for us to understand the quantum information better. So that's why I think maybe it's a good idea to report some of the unusual features when we talk about the thermodynamics as strong coupling, by which I mean the strong system and back coupling. It does not mean the strongly correlated system like that. So since it's kind of unintuitive, so sometimes we have to abandon what we have learned from the textbook and kind of understand the thermodynamics from the new beginning. Okay, this series of work is in collaboration with Professor Hu Bile. You might have know him from his work on the non-equivalent field theory or quantum field in curved space-time, especially in the 80s. He has done tons of work on quantum field in curved space-time. And he has published 2 books from the Cambridge University on these 2 topics. So if you are interested, you can find kind of a sense of his work in those 2 books. Okay, yeah, because this topic involves a lot of new ideas, and you will know that in the due course that the thermodynamics as strong coupling is not as universal as the conventional thermodynamics. So in most cases, we have to discuss it case by case. So that's why I will choose the simplest case to introduce the whole idea. And I will use the Gaussian system because I think every one of you are very familiar with the Gaussian system, like the Harmonic oscillator or the field. And we will try to look into the thermodynamics as strong coupling from the microphysics viewpoint. So let's give you some motivations. The first one is pretty pedagogical because as a student in the NTU, most of you probably will develop, will kind of contribute your future career in theoretical physics. So the most often question you will ask is, what if? What if we change something? What will happen next? So here the what if means that from the textbook, you probably know that the conventional thermodynamics are formulated based on certain assumptions. So here we want to ask, what if we remove those assumptions? Then how the thermodynamics formulation will be changed? So this is the first motivation why I dig into this topic. The second one is more related to the current technological advance because recently we are working into a some microscopic system like the nano machine, or even the QD or circuit QED. In those cases, the quantization volume is relatively small compared with the usual unbounded system. So in those cases, you will learn later that the affected coupling will tend to be larger than the typical unbounded macroscope system. So that's why it seems a good time to look into the system with stronger interactions. And if we are looking into those actions, then it's necessary to study its thermodynamical behavior. So basically, that's the whole motivations we are doing this topic. So let's review a little bit what we already know about the conventional thermodynamics. Yeah, so here's I should have written it as the thermodynamics, not the. Okay. We know that at least in the conventional equilibrium cases, we know that the system usually coupled to a certain bath with some temperature beta inverse, and the bath plays a minimal role. It usually provides some heat to the system, and basically you don't need to worry about that the bath will affect the dynamics of the system. So recall that when you formulate a thermal state of the system, you never see or you never find any information about the bath. The only information you can see related to the bath is the temperature. So you don't need to worry about the dynamics of the system modified by the bath. And the bath try to keep the system at some fixed temperature. And we also do not need to worry about the back direction of the system to the bath. So essentially, bath, there seems to know essential role of the bath in the whole formulation. And we know that the system will be so-called equilibrium distribution, and this described by this density metric. Here you see that we only need to know the Hamiltonian of the system. Then, as I mentioned earlier, that the only and the universal parameter entered about the bath enter the system is the temperature. It's the inverse temperature of the bath. And of course, this density metric describes some kind of mixed state. And in the context of quantum entanglement, you probably know that it can quantify the correlation between the system and bath. But however, at least in the past, we never, in the past 10 years, before past 10 years, we never put too much attention about how the correlation between system and bath will affect the thermodynamic behavior of the system until quite recently. So that's a very interesting topic we can focus in the future to see how the entanglement play any roles in thermodynamics. However, in the past, we never paid attention to this one. So we didn't see the correlation in the traditional formulation of thermodynamics. Okay, why we can do that? Why we can ignore the bath dynamics? Because it based on a few plausible assumptions in the macro system, in the macroscopic system. The first one is that typically we assume that we formulate this system in so-called thermodynamics limits, which means that the degree of freedom of either the bath or the system are very large. Especially the number of degree of freedom of the bath is way larger than the number of degree of freedom of the system. And we also assume that the system bath is very weak. But why can we make this assumption? At least for the macro system, we can try to understand this in this way. Since the number of degree freedom of system is usually much smaller than sorry. Since the surface area of a macroscopic system is way smaller than its volume. And we also know that typically for classical macro system, because only its outer surface will in contact with the outside environment. So we usually will kind of say that the interaction strength will proportional to the surface area. So when we make this comparison, we will know that for a typical macroscopic classical system, the interaction with the environment is not strong compared with the system energy itself. So that's why we draw this conclusion and say that, okay, we can make a weak coupling assumption. However, this kind of argument may need revision when we look into the smaller or when we look into the quantum system involving quantum field. Because you know that quantum field is everywhere. We have no way to effectively exclude the quantum field from the system, from entering into the system. So this kind of partition is meaningless in terms of quantum field. So since for the macro system, this assumption is these assumptions are quite plausible. So we usually draw a conclusion that the interaction between system and mass is negligible. So we don't need to worry about their interacting dynamics. And also one of the most useful feature we got from this conclusion is that we can easily separate the total either momentum, total energy or total number of particles or total number of states into this simple partition. Just divide, just write them as sum of each subsystems. And if you recall for example, in the Rice's book, how he showed the derivation of the entropy or derivation of the density metric, you will see that this kind of argument is used very often, even in the Lennox book. Once we use this equation, then the whole argument will be simplified a lot. And we can get a really universal argument. And this argument will, most of the time, independent of detailed system. So when we trace back the whole argument, we will see that, in fact, the weak coupling plays an important role to support this kind of argument. Okay, but so far everything seems quite reasonable, and also accept it quite easily. But if you think a little bit more, you'll find out it's a little bit strange. For example, when we put the system in contact with the bath, then how this system will come into so-called thermal equilibrium state? Because if their interaction is so weak, in principle, it will take a very, very long time. At least from the open system viewpoint, you will find out that it will take a very, very long time to reach the equilibrium. But in reality, it's quite, the thermal equilibrium is established quite rapidly. But there's more than one reason to understand this one. So there are more than one schools of formulation for the equilibration of the system. Here we take the open system viewpoint. The other one is closed system viewpoint. In those cases, you probably have to resort to the argument of chaos, that kind of things. But that's the outside scope of the present talk. Here we will understand the whole thing in terms of open system viewpoint. Which means that we literally look into the dynamics between the system and bath. Okay, so back to back to here. So if we really stick into the weak coupling, then we will have trouble to understand how the initial thermal equilibrium of the system is established. For example, here I give you a very extreme example. You will see quite often in the context of cosmology. Because sometimes people argue that, okay, we can easily have some kind of thermal graviton bath. Well, but if you follow this argument, you find out that it's very difficult for the graviton to reach thermal equilibrium because its cross section is so small. So the interaction between the graviton cell interaction or interaction of graviton with other quanta is quite ineffective. So in principle, on top of that, because the universe is expanding, so it's very hard to see how we can have a thermal graviton bath or thermal graviton soup, whatever you call it. So this gives you a very extreme example to see something very strange when we stick or when we look into the weak coupling tool literally. And later I will try to give you some. I hope if we have time, we'll kind of to see how this thing happens from the viewpoint of open system. Okay, so since we know, in the first part, I kind of reviewed the idea of how the conventional thermodynamics is formulated based on certain possible assumptions. And now we try to remove one of the most important assumptions in the formulation. So we see that what will happen if we let the interaction between system and bath is not weak, even finite. We don't need to strong. We only need to be finite. Okay, at least in the earlier slide, I argued that since the system bath argument, since the system bath interaction is weak, so we don't need to worry about the evolution or dynamics of the bath. But when the coupling is not weak, then we have to pay attention to the evolution of both subsystems. So, in principle, the bath will start evolving away from its initial thermal state, and of course, their evolution will affect one another. So, make the whole thing very complicated. But this is also the fun part because from this point on, the thermodynamics. We really need to worry. We really talk about the dynamics in the thermodynamics. In the past, it's not. We shouldn't call it thermodynamics because we didn't see the dynamics part in the word thermodynamics. Here from now on, we really have to take that part into theory. And so it's a good idea to go beyond the equilibrium formulation. And in fact, you will find out that even for the simplest case, for example, if I have a harmonic oscillator coupled to some thermal field, then you will find out that if the interaction, the coupling is not weak, then the harmonic oscillator will reach some final equilibrium state. But you find out that the corresponding density metric does not take the Gibbs form. So, which means that it's not given by this simple expression. It turned out to be quite complicated, depending on the detail of the system configuration. But it will depend on coupling constant, depend on the oscillating frequency, and so on. So here, the first difference is that I want to emphasize is that equilibration is not necessarily equal to the thermalization. And you can show that only in the limit, that the coupling constant approaches to 0, then this density metric will approach it to this form. So this example gives us a very nice description about these two ideas. And you'll see that I will not show here, but if you look into the literature, you'll find out that the difference will be greater if the interaction between system and bath gets stronger. So this is the first lesson we learned that when we go beyond the recoupling, we have this difference, and this will sometimes cause some trouble. Because if you recall the situation when you do some problem, which deal with some thermal system, the first thing you do is that you write down the thermal state of the system. Because you know this system is definitely in this state. But if the company is not weak, you have no way to do that because you don't know what state the system will be. You have to do some extra calculation to find out how the system will relax into, what state the system relaxes into. So this gives you a few additional, I would not say trouble, but you have to be careful, a little bit careful when you describe system strongly interacting with the bath. So that's why I say we will no longer have a priori knowledge about the system state. And also due to a strong coupling, the interaction energy will be comparable to the system energy as well. So this is the second. This will cause a lot. This phrase or this statement will cause. You will see that it will cause essentially all of trouble we will meet, right, in formulating the thermodynamics and strong coupling. Also, another thing you might want to pay attention to is that if the system is small, then you probably know that at least when the number of degree freedom is sufficiently large, we know the fluctuations tend to be small because the fluctuation, the ratio of the fluctuation over the mean value is kind of 1 over square root of the number of degree freedom. And if we extrapolate this argument to a very small n, we will see that we will expect that when we deal with a small system, the fluctuation becomes very important because it will give a comparable contribution to the mean value. So that means that it's probably not enough to formulate the so-called thermodynamic laws in terms of the mean value. We have to put into extra elements about the fluctuations in order to properly describe the behavior of the small thermodynamic systems. Okay. Earlier I said that when the interaction energy is comparable to the system energy, it will cause lots of the ambiguity. This ambiguity will be shown in the definition of state function. Okay, I will skip this part for a moment. Okay, why it will cause such an ambiguity? Let's see that when the interaction energy is non-negligible, then the total energy or total Hamiltonian effect is expressed in terms of the system Hamiltonian, fast Hamiltonian, and their interaction term. And we cannot ignore this term. So the total Hamiltonian is not sum of this one, which also means that the total energy will not be the sum of the system energy plus the energy of the bath. But you may ask, what's the big deal with this one? The big deal is that if this term is a contribution of this one is non-negligible, then how will you distribute this one among the system energy and the bath energy? Because let's see. Okay. Here we consider the simplest case. When some systems are in the thermal equilibrium, somehow we have the whole thing in thermal equilibrium. So the system and bath form a closed system, and they together is described by this standard Gibbs form. This would be the easiest case to study the ambiguity of the definitions of the thermodynamic potentials or thermodynamic functions. So I want to okay. So because in this case we have a kind of well-defined, at least the partition function is well-defined. Usually once we have a partition function, then we can use partition function to derive the entropy or the internal energy or any other thermodynamic function we are interested in. Well defined partition function is not it's not easy task. If you don't believe it, you can try to formulate some partition function for an arbitrary system. You can see that it's very difficult because usually the density measuring of an arbitrary system do not have a simple form like this one. It does not even take the exponential form. So in those cases, you would have no idea how to write down a partition function for an arbitrary system. But for the closed system in a certain state, this can be done. Okay, so that's why we start with a closed system in which the system we are interested in is strongly interacting with the other part, which we call it bath, denoted by B. And okay, we can define. Of course, we can easily define the partition function for the free bath. And we suppose the corresponding partition function of system will be obtained by divide the total partition function with the partition function of free system. We suppose this will be the partition function of our system, of the system we are interested in. Then we can use this partition function to derive, for example, the entropy or to find the internal energy of the system. And this essentially is the standard procedure you will see in the textbook. Except that in the textbook, we don't care about the interaction energy here. And in the recoupling, we find out that we can express the internal energy either in terms of the partial derivative of the partition function, or as the expansion value of the system Hamiltonian. And also the entropy, we can find out that at least for the recoupling case, these two definitions are equivalent. So that's why. So it means that we can either write the binomial entropy in terms of the trace of the log rho, or the certain partial derivative of the free energy or partition function. Okay, so in recoupling, we don't have any problem or ambiguity about how we define the thermodynamic function, because we can either use this way or use this way. But if the interaction time is not negligible, you will see that these two definitions are not equivalent. And why? Because if we look into if I take the internal energy as an example, we will find out that if we use this approach, then this internal energy, in fact, include a lot of terms other than the system, other terms than the exponential value of the system Hamiltonian. You know, where do these terms come from? And if you dig into the structure of this system, you find out that the culprit is the interaction term. Because we cannot ignore the interaction Hamiltonian. And this term, if we ignore them, then all these terms will vanish, and we will come to the equilibrium formulation. But when we cannot ignore the interaction term, then these three terms will have a non-trivial contribution, make it both different. So the question we want to ask is, which one describe the system better? So far, this question is still open. We have no idea. In fact, you'll find out that we can formulate, we have essentially infinite number of ways to formulate the thermodynamic function when the coupling is not weak. And so we have to resort to certain consistent relations to see whether, but the choice of those consistency relations is kind of personal preference. For example, sometimes some people like to preserve the well-known thermodynamic relation like free energy equal to U minus temperature times entropy. Then someone else choose different considered relations. So this difference also will make the will give you a different set of the thermodynamic functions. So that's why so far we do not have a definite, or we don't know which set is physically more reasonable. Those probably has to be determined by the experiments. But even that, I still doubt that even we have some experiment to measure this quantity, we can still not fix the thermodynamic, fix the so-called good set of the thermodynamic function. The idea is that because when the coupling is strong, certainly sometimes it's very difficult for you to distinguish between the so-called system and red, because they are all mingled together. And so when you perform certain experiments, sometimes it's very hard to see the experiment measure so-called system part, because sometimes this measurement will accidentally involve certain contribution from the back. So I worry that even we have specifically designed certain experiments to try to distinguish these sets. The conclusion may depend on how you perform the experiment. And this kind of thing has been, well, we have seen this kind of situation when we try to determine so-called the momentum of the EM field when the dielectric constant is involved. If you look at the literature, there has been some debate about how to define the momentum of the EM field in the dielectrics. And there are two alternative definitions. And they're all correct. They're all supported by the experiment. So that's an example that even we have experiment, we still maybe have no way to determine which is good set of which set is good, which set of thermodynamic functions is good. Probably we don't need to make a distinction, because we may use a different set for different contexts. So far, this idea or argument are all. Okay. Here, I give you some example about what can go wrong if we use either this set or this set of the definition of thermodynamic function to give you some idea that we have to be careful when we choose this one, because sometimes it will cause some unphysical result. For example, if we use this definition of internal energy, and we compute the, for example, a lattice of oscillator, couple oscillator, we try to determine its heat capacity. And we look at the behavior of heat capacity at very low temperature. For such a simple system, because there are no degeneracy, so we expect that when the bath temperature approaches to zero, the whole system should stay in the unique ground state. And if that's true, then we should expect that the entropy of this system will go to zero, or at least some positive number. But if we use this definition to compute the heat capacity and try to examine the behavior of heat capacity close to at very low temperature, people have shown that the heat capacity will become negative when the bath temperature close to zero. This is very strange, because that's not comply with the simple argument I offered a moment ago. However, if we use the one normal entropy to do the calculation, then we find out that it behaves quite nice. And if I use this definition to compute the heat capacity, we find out that it will become negative at low temperature. So in a sense, it's not critical. But if we use this definition sometimes called thermodynamic entropy. If we use this definition of entropy to compute the entropy for that system, then we find out that people have shown that it will go to 0 very nicely. But on the other hand, let's see if we use this set of definition to repeat the earlier calculation. And this definition of internal energy will give a nice behavior of the heat capacity at low temperature. However, if we look into the entropy, we will find out that this entropy will not go to 0 when temperature goes to 0. The reason is that when you have an interacting system, the system and the bath can have some non-zero entanglement. So non-zero value of this one only reflect the fact that the system and bath, in that case, is entangled. So it seems that at least I'm not sure whether the von Neumann entropy can truly tell us the thermodynamic behavior of system at low temperature, or it implies that we have to take a really serious consideration about the role of entanglement in the formulation of the entanglement in the thermodynamics. So you can see that both definitions they behave nicely in certain set of the measurement, but it may behave badly for the other set of a physical quantity. So that's the example I want to create for you to see that why we want to find a good set of the thermodynamic function which can give as many as possible reasonable results for all kind of measurement. But at least so far, these two definitions don't work for all cases. And to be more specific, I can show you the behavior of the internal energy calculated by the expression value of the system. Because this blue line will be the result you obtain from the conventional thermodynamics. You can see that it approaches to some fixed value quite nicely. But with the stronger system and bath interaction, you see that the curves start deviating from the value predicted by the equilibrium thermodynamics. Because when also we see there's a very interesting qualitative change in the behavior in this part. Because from the conventional thermodynamics, you will see that at low temperature it is exponentially approached to the fixed value. But when the coupling is strong, it will approach the fixed value in an algebraic way. The mathematical argument is that a strong coupling, the dominant factor in the formulation is no longer temperature. The coupling constant or the system or the parameter of the system will come into play, so that you will make it approach to a fixed value in non-exponential way. So this is an interesting qualitative change in the thermodynamic function, at least in this case, the energy at very low temperatures. And also, the other qualitative feature you would like to pay attention to is that okay, you know that at least for the harmonic oscillator, for the free harmonic oscillator, we know that its energy level is discrete, it's equal spacing. So you will take some energy for the oscillator to transit from one state from one level to another level. But when the oscillator couples to the bath non-weakly, we will see that its energy level become continuous, except the ground one. Ground one is still unique, like delta function. But for the higher levels, we cannot say it's levels anymore because it becomes a continuous distribution. But the peak is still close to the original positions of the level with a little bit shift, like the length shift. But at least it's apparently that it becomes a continuous one. So it means that the transition or the behavior of system under this consideration change totally from it's free or from weak coupling case. So people usually say that it changed from the gap system to a gapless system because in this case, since due to the continuous distribution, the transition is so easily. And also because the peak has a finite width, this reflects the finite lifetime in the language of MO, or or you can say that the width is related to the time scale for it to decay, for it to decay or stay in the original levels. So you see that there are quite a lot of difference when we allow the interaction to be strong or to be non-weak. And we also have to be careful when we formulate the problem. We have to kind of remind ourselves pretty often that we cannot use the old way of thinking, always of thinking. Okay, I have 50 minutes to. Okay, one of the very interesting features when we deal with the thermodynamics, in the non-equilibrium context, is the new understanding of the fluctuation dissipation relation. You probably will wonder what's the big deal with this one, because Kubo has derived it very early, and you use a very simple argument in terms of the linear response theory. But have you ever wondered why that relation is called fluctuation dissipation relation? And what's the physics of this relation? At least for me, I've been puzzled by that because I don't see. Because sometimes people argue that this relation describes the balance between the fluctuation and dissipation. But at least from the derivation based on linear response, I don't see how they draw that conclusions. But in the context of the non-equilibrium formulation, then we can pretty easily see why we can say it that way. Also, we can understand its physical meaning better. Also, more interestingly, if we allow the interaction to be non-weak, then we will see some marvelous feature of these old relations. Okay, before we look into that relation, we first see how because before this point, I have mentioned that even I have a simple system like harmonic oscillator coupled to a thermal field. This oscillator will come to equilibrium, but how does it happen? And what actually happens during this process? So these are what I will talk about in the following 15 minutes. Okay, the first thing here I show you three main features during the relaxation process. The first one is stationarity. The second one is the emergent of the emergency of the FDR relation. I will explain why do I call it emergence. Then the third one is the energy balance of energy flow. Okay, why I want to mention this non-stationarity. Physically, you can understand that when I have a system which is initially non-equilibrium with a bath, then then you will be sure that it will evolve. So we have some kind of non-equilibrium evolution. Then this evolution, then if you look into the, for example, the 2-point function or correlation function of the correlation of the system, you know that the correlation of system is not stationary. It means that it depends on true time. It does not depend on the time difference. However, as the system evolves to the final equilibrium state, you will find out that the non-stable component is suppressed by this relaxing behavior. And this is nice because it allows us to perform the Fourier transform. If we end up with, if the 2-point function is stationary, then we can perform the Fourier transform. And this seems to give us hints that something like FDR can be formulated at a later time. Okay, after some work, you will find out that actually, given the we can really write down the FDR fluctuating dissipation relation of the system. Here, this one is the Hanna function, means the Fourier transform of the and of truth and the commutator of the system's canonical variable. And this corresponding retardatory function, the systems defined for system canonical variable. We find out that indeed at later time, because I mentioned that the relaxation will suppress the non-stationary component of the 2-point function, so that at later time we can perform the Fourier transform. And we can really show that we can write down this relation. So this relation is only shown at later time. We don't have this kind of relation during the transient process. So this is quite different from the Cobo's original formulation. Because Cobo's original formulation based on the equilibrium formulation. So generally, essentially applies all the time. But in the context of the non-equilibrium formulation, we don't have such a formulation until the late time. The funny thing is that in this expression, this factor depends on the initial temperature of the bath. And when even though I don't show it, but I will tell you that this formulation still applies when the interaction between system and bath is strong. So you might ask, what's the big deal with these two statements? Okay. Let's jump here. Let's jump to this slide first. Okay. The striking part is that in the beginning of the talk, I mentioned that when the system and bath is not weak, the final state of the system is not thermal state. And here I tell you that I can formulate FDR at the final state. Then so you may wonder why in the FDR system, sorry, in the FDR system, the initial temperature of the bath is shown here. The second thing is that it turns out that this formula, this expression also applied if the system is modeled by a nonlinear oscillator. And if this nonlinear oscillator has a stable, unique equilibrium state, then I can derive this equation non-perturbatively. So this, and also I mentioned earlier that this expression to derive the derivation of this relation does not depend on the system bath strength. So these three statements seem to imply that the FDR has maybe more general than we understand based on the coarse renal formulation. And it seems to have some interesting connection about the existence of the equilibrium state, because this also holds for nonlinear system, which has a unique equilibrium state. And so it's worth to have more thought about how much information we can take from this FDR. At least for now, it's way much more than what we originally expected. Okay, then next, even we know that this relation has some interesting implications, but what is physical meaning? Can we have a way to understand its meaning? Okay, here a good way to do is try to if we try to look into the process of relaxation of the example I mentioned earlier, that I have a Hamel oscillator coupled to a thermal bed. If we look into its relaxation process, and we try to examine the energy exchange between the oscillator and the bed. And two major channels of energy exchanges are these two. This essentially describes the quantum noise of the bed, the work or the power delivered by the quantum noise of the bed to the oscillator. And this second term tells you that the energy lost by the oscillator due to dissipation. I have no time to explain why we have these two types of the back reaction, but at least intuitively, it's quite easy to understand that when the oscillator coupled to the bed, the bed will kind of pump energy to the oscillator. But on the other hand, because the oscillator is doing some non-trivial motions, and you expect that some damping will happen, and this damping will kind of drain the energy of the oscillator back to the bed. So it's intuitively quite possible. Of course, there's some derivation about this one, but I don't have time to show it. I have only 5 minutes left. Okay, so from this one, we try to see how these two quantities change with time when the system evolves to final equilibrium. And from these two plots, from these three plots, we see that this power delivered or done by the work rate done by the quantum noise from the bed. You can see that it rapidly approaches to the constant value in later time. But and this energy dissipated by or power dissipated by the oscillator to back to the environment of bed. It also approaches to a fixed value, but with a longer scale. This time scale is order of the relaxation time scale. But somehow the fluctuation or noise is saturated much more rapidly. And if we add them together to see the total net energy exchange between the oscillator and the bed, we see that it approaches to 0 at late time. And this fits the physical description of the equilibrium, because which means that there's no net change in the system over bed. It means that they come, whatever interaction between them should come to some stable state. So that's why the net energy, there's no energy flow from one component to the other. They are all bands. So this result is reasonable. But what does this result can tell us about the FDR? Okay. When you try to show the late time energy balance of these two powers, you will see that this two equality, or of these two equal signs will be possible only if the FDR of the system are satisfied. So of course, in the derivation of the FDR system, we need the FDR of the vast. Okay, so it means that, the physical meaning of the power is, the physical meaning of this expression is the power delivered by the fluctuations, by the noise. And this one is the power delivered by the dissipation. So this expression just tells us that when the FDR applies, the power due to the fluctuation is balanced by the power due to the dissipation. So that's why it gives a better or clear picture of why we can call FDR. How we derive, how the fluctuation dissipation relation, how these two terms is incorporated into the terminology or the name of the FDR. So turn out it can be understood as the energy balance due to the fluctuating component and the power due to the dissipation component. Okay, so I have no time to tell the details. Well, so if you're interested in that, you can find out in this series of papers, which Professor Wu and I try to understand the FDR from the non-equilibrium and viewpoint. And okay, finally, I will use 1 minute to tell you some interesting implication to the zeroth law when the coupling, when we deal with the non-weak interacting thermodynamical system. Okay, in the past, or if you look up the entry of the zeroth law in the Wikipedia or in the textbook, you find out that usually there are two equivalent ways to describe the zeroth law. It says that when we let A in contact with B, and if they reach a solid equivalent, then we let the C in contact with B. If they also reach a solid equivalent, then we expect that A and C will also in so. If we put A and C together, then there will be solid equivalent. And more strongly, we say that they have the same temperature. Well, this is pretty okay in the context of the dimensional thermodynamics because the coupling is weak. And if you follow the textbook, you'll see that we have a way to define the universal temperature scale. That's the absolute temperature we use. But when we deal with non-weak coupling, the first thing I tell you is that even if these two subsystems come into equilibrium, they will be in a state different from the thermal state, or different from the Gibbs form. And this means that from the expression of that thermodynamic, from the expression of that density metric, we have no way to extract the information of the system temperature. If we try to do that in an effective way, we will find out the temperature we define will depend on the coupling strength and system parameters. Then also, I mentioned that a strong coupling, the equilibration is not equivalent to thermalization. So you can see that this truth statement will need some revision when in the context of strong coupling thermodynamics, because we cannot say they are thermal equivalent, and we don't have any simple parameter to quantify or to describe this zero law. In the old times, we can use the temperature to kind of mark or benchmark the zeroth law. But we can no longer do this when we deal with a non-weak coupling. So that's why, yeah, it will cause a little some trouble, or the zeroth law become less informative in the context of strong-carbon thermodynamics. Okay, so this is only part of the entry phenomenon you will see for the strong-carbon thermodynamics. I only give you some introductory idea about what you will expect if the interaction is non-weak. So hope that next time I can tell you the next part. Okay, so here's the conclusion. Okay, let's review what I have mentioned to you from the beginning of the talk. The first thing we see that when we allow the interaction to be non-weak is that we need to look at the whole thing in a dynamical viewpoint. We have to really look into the evolution of the bath. We cannot ignore the interaction between the bath and the system. And then, due to the comparable contribution between the interaction energy and system energy, we find out that we have trouble to give a unique definition about the thermodynamic functions. And this, of course, will affect how you write down the thermodynamic law. And this non-weak interaction also makes a distinction between the equilibration and thermalization, at least in the framework of the system. And I also mentioned that when the system is small, you have to be careful about additional contribution from the fluctuations, because it will give a contribution comparable to the original mean values. And this also affects the way you will formulate the thermodynamic laws. And also, since the larger fluctuation will be involved, so sometimes we will in the past we usually easily resort to certain Gaussian approximation to formulate a system or formulate the problem. But when the fluctuation is large, you have to be careful that certain non-Gaussian feature will come in. Because you can quite easily to expect this one, because if you recall the field theory, the energy density of field is quadratic in field operator. So when we deal with the fluctuation of the energy density, we usually will worry about the quadratic expression of the field operator. And if we want to deal with the third moment of the energy density, then we will deal with the sixth power of the field operator. So their expansion value is not zero, not like the up power of the field operator. Because up power of the field operator for a free field is zero. But the up power of the energy density is not, because it involves sixth power of the field operator. So it's not. So you can see that this is how the non-Gaussian enters. Because the third moment of the energy density is not non-zero. And also, you might wonder whether it's easier to deal with the fluctuation if we have an operator formulation for the thermodynamic system. And well, if we have this one, then it will be quite easier to do this one. However, it's not easy to write down the operator formulation, because most of the time we start the whole thing from our traditional understanding of the thermodynamics, which is based on the mean value. So it's hard to extrapolate the final knowledge from the mean value to the operator. The operator formula provides the final knowledge than the mean value. So it's difficult. And also a very interesting, there are two additional topic which are the focus of the research is that is there any way to define the work in the context of quantum system? Because usually we don't have the definite way to define a path for quantum system. At least from the idea of path integral, we don't have a definite path. We have multiple paths, all possible paths. So in that case, how do we define the work for a quantum system? Also, yeah, the entanglement. What's the role of entanglement in the thermodynamic system? This is something people are doing research on this part, but it's not. It's still in a lot of progress right now. Okay, so that's all for today's talk.
Any questions？
这个东西反正基本上是不是那么直觉，所以有时候乍听之下有人听那边不飒飒，因为跟你以往的认知不太一样，所以有时候会有一些奇怪，到底是怎么回事？所以这是有时候真的会需要再多想一两下。所以第一次听这个 talk 没有问题，我这是理所当然的，因为可能都傻掉了。
就是你说那个 strong coupling 的时候，它的 behavior 就不一样。那
对，
有没有一个点说怎么样算是 strong coupling？哦，
通常啊，对，通常比如说RCA的这 case 啊，这个 strong coupling 的定义还蛮简单，就是通常我们会说它的 coupling constant， 不，它的那个 damping constant 可能跟它的那个 RCA strength 差不多同一个 order 也可以，或者说更简单，就是说只要你这样的 interacting system， 它的 interaction energy 跟它的 system energy 大概同一个 order 就已经算非常非常 strong， 甚至不用同一个 order， 只要不是无限小的话，这些效应就会慢慢跑出来。
那个效应不一样跑出来是它会突然就 sudden change。
也没有到 sudden change， 就是说，比如说像我刚刚提到一个例子，就是说 ，OK， 我有个 free RCA 的，只要我们只看一个 free RCA 的话，它 energy level 是 discrete， 所以你要 excite 这个 RCA 的话并不容易，需要一个 finite amount of energy。而当它 cover to 那个 band， 然后是 non-weak 的时候，你就发现它这个原来是 discrete 的 energy level 就开始，一方面变胖，然后一方面又 shift 一点，然后又通连起来。那这个情况下，其实很容易就可以 excite 这个 system。所以可以期待，在这个情况下，它这个有 coupling 跟没 coupling， 或极弱跟 finite 的时候，它的那个 behavior 就不太一样。对，所以它不是 change， 它其实你可以只要把这个 coupling 把它越弄越小化，你发现它就到最后又几乎回到那个原来的那种 case。对，所以它不是杀的。
Any other questions?
我是想
我感觉到好像你们现在还在印那个 deconstructing move， 你在 deconstructing 那个 thermodynamics 的。
某种程度是
thermodynamics 的，
对
那些 formulation，
对，
那是非常的一个假设，对不对？
对，你不是假设，就是说，假如我们把以往的一些假设都拿掉的话，
对啊，
那这个东西会变什么样子？对，我们现在看这件事情。对，
所以你刚刚你这个 conclusion 这个否定句大过肯定句。
目前是因为大部分，我就希望让大家知道一下，说它会跟传统的有什么不一样，所以我会举出很多以前你们都熟知的例子，来告诉你说，哎。这样不行了，它会变什么样子？哎，那样不行，会变什么样子？所以没错，否定句大过肯定句，没错。
这是我认为这是 deconstruction。
OK。
所以你想一下，就是像我的思考方式是说，这个很辛苦，因为你把整个那个 statistical mechanics 的上层的 statistical mechanics 的那些 formula 都。因为你remove掉它最重要的一些那个，对，最重要的那个假设，
对，就是说，我们现在从等于说，因为这种都有点像一对多，
对啊，
传统的那个生物单位是算一，然后你到多的时候，到底哪个是好的 approach？ 对，这没错，这样讲，这的确是一个，
所以我就开始怀疑一件事情，就是说， 因为对于某些问题，尤其像很小的系统，比如像我们在研究的那个 QED，
对
，OK CQED，
嗯，
对不对？我们不会想要用那个 thermodynamics 去 formulate 它。
对，
哦，
对，
呀，通常这个东西一定要东西大到某一个程度，
也是，
东西大到某一个程度，然后我觉得搞不好可以 apply 到那个什么 ，apply 到那个 information theory 上面去，
也是有可能，
有这个，
对，所以也是这个原因，我
嗯
觉得我想说在龚老师这个 QIS 的管理不在这个 QIS 的 seminar session 里面谈这个东西，也是因为希望把这些东西连接起来，而且也希望说，当这两个连接起来的时候，我们对那个 entropy 这个意义啊，有没有更好的了解？不过再回到你刚刚之前那个问题，还有一个问题就是说，没错，当我们在讨论一个非常小系统的时候，我们通常会像我刚刚提到，我们会真的从 dynamical viewpoint 去探讨这个问题，而不会去真的去一下就跳到 thermodynamics。
对。
可是我们也会反过来问，就是说，哎，到底这个 thermodynamical behavior 可以把它 push 到多远的程度？可以push 到什么程度？因为对，这也是我们想去试的，看它到底limit在什么地方。
是啊，
对，
我听了。
还有其他问题？对啊，所以这大概就是在说，就是说，如果说我们现在处理一个 quantum 的这个东西，在这么小的 scale、这么小的 system， 我们通常都是看它的dynamics，不管thermodynamics会怎么样。那现在就说好，那你的系统要多大？啊，那你的情况要在什么样的情况？这样子thermodynamics才可以 apply。那这当然是另外一种 question。
对。
好，还有没有其他问题？好，那我们待会儿会有 tea time 啊，那还可以跟我们的 speaker 一起讨论一下啊。好，那 let's send the speaker again。好，那去帮他弄一下，请大家签一下名。